In the previous series of lectures, we were discussing natural convection. Okay. If you have a heated object in a colder fluid, the fluid close to the object gets heated up, has a lower density and therefore rises, and the fluid from far away comes in to fill the gap, and this acts as a mechanism of energy transfer due to convection, which is in addition to the molecular diffusion mechanism, and this can be the dominant mechanism in many practical applications. We looked at this using a series of approximations, the Boussinesq approximations. The density variation is linearly proportional to the temperature variation, where the coefficient of expansion, thermal expansion coefficient beta, is the proportionality constant. Density was replaced by the density, ambient density everywhere except for this driving term. If you do not have density variations in the gravitational buoyancy force term as well, then there is no flow. So, you have to include that, but everywhere else the density was neglected, and I showed you that for gases this is a good approximation if the difference in temperature is small compared to the absolute temperature. Okay. Similarly, we had neglected the viscosity everywhere except we had considered the viscosity to be the ambient viscosity, and so also for the thermal diffusivity. With these approximations, we got a series of equations. Okay. The mass conservation, momentum conservation in terms of the dynamical pressure difference between the pressure and the hydrostatic pressure if there were no temperature variation, and similarly we got the energy conservation equation. We scaled these to find out what is the characteristic velocity that is generated. Okay. And this characteristic velocity is square root of the characteristic length, gravitational acceleration, beta, and the difference in temperature T naught minus T infinity. Okay. So, that is the characteristic velocity. Substituted that into the conservation equations and done the scaling. Okay. And we got equations in terms of the dimensionless group called the Grashof number. Okay. This is Grashof number is the square of a Reynolds number based upon the characteristic velocity and the characteristic length scale. Okay. That Grashof number appeared in the momentum conservation equation 1 over gr power half. Energy conservation equation, we had a 1 over Prandtl number times Grashof power half, because in the energy conservation equation there is the thermal diffusivity instead of the momentum diffusivity. Therefore, the dimensionless group has to be multiplied by a factor which is basically thermal diffusivity by momentum diffusivity times 1 over Reynolds number. Okay. So, those were the scaled equations. Okay. Note that these equations, they contain the momentum equation contains a temperature dependent term through the body force. Okay. The momentum equation contains a temperature dependent term through the body force, and the temperature equation contains a velocity dependent term through the convective term. Okay. The temperature equation contains a velocity dependent term through the convective term. Okay. So, those are the equations, and then we were simplifying them for the case for a two dimensional flow. I should note that this can well be applied to three dimensional flows as well. Only thing is the algebra is a little more complicated, but the principle is the same. Okay. So, whether you apply it for two dimensional flows or three dimensional flows, the principle is the same. The algebra gets a little more complicated. Mass conservation equation, okay. Partial Vx by partial x plus partial Vz by partial z equal to 0. Momentum conservation in the x direction, momentum conservation equation in the x direction. Okay. Vx partial Vx by partial x plus Vz partial Vx by partial z, pressure gradient, viscous term and gravitational term, and this is the z momentum. Once again, convective term on the left, pressure gradient, viscous term, gravitational term, and this is the energy. Left side is convective term, right side is the thermal diffusion or the thermal conduction term, okay, del square of T. Now, we were considering the limit where the Grashof number is large. Okay. We are considering the limit where the Grashof number is large. Okay. in the limit of large Grashof number, right, you might think that you can just neglect the diffusive terms altogether and just solve the rest of the equations. Okay, you can neglect the diffusion term altogether and solve the rest of the equations. If you do that, the equations transform from a second order to a first order differential equation. You cannot satisfy boundary conditions. Physically, if you do that, there is no mechanism for diffusion. Therefore, there will be no heat transfer from the surface, because at the surface convection is along the surface. There is no velocity perpendicular to the surface. Therefore, there can be no convective transport perpendicular to the surface from the surface to the fluid. For that, we need diffusion. And we know what to do in such a case. There has to be a smaller length scale, a boundary layer thickness, within which the convection and diffusion are comparable, even in the limit where the Grashof number goes to infinity. The thickness of that layer goes to 0 as the Grashof number goes to infinity, in such a way that convection and diffusion are comparable within this region. So, we did that by scaling z by another coordinate, okay, by LC times delta. Delta star is a dimensionless boundary layer thickness. Okay. Delta star is a dimensionless boundary layer thickness. The streamwise coordinate, in this case x, was scaled by LC. Velocity by Vc. Velocity in the z direction perpendicular to the surface has to be determined from the mass conservation condition. Okay. The scaling for that has to be determined from the mass conservation condition. From that, we found that the scale for the velocity Vz perpendicular to the surface is delta times Vc, where Vc is the characteristic velocity. Okay. Okay. So, now we substitute these scalings into the conservation equations. Okay. Okay. We substitute these scalings into the conservation equations. Okay. So, I get scaled Vx partial Vx by partial x plus Vz, Vz star. Okay. Vz star, okay, Vz star is equal to Vz by Vc will be equal to delta times Vz plus, okay, where Vz plus is the scaled velocity, okay, and z star is equal to z by Lc delta is equal to z star by delta. Okay. Sorry, z plus is z star by delta. Okay. So, z star is delta times z plus. Okay. So, first term here I have delta Vz plus, okay, partial Vx star by partial, okay, z plus, and I have a factor of delta coming out, okay, because Vz star is equal to delta times Vz plus. Okay. Okay. Therefore, basically I have to substitute, okay, Vz star is equal to delta Vz plus, okay, and z star is equal to delta z plus, okay, is equal to minus, okay, partial p partial x star plus, okay, the 1 by Grashof per half into partial square Vx by partial x square plus 1 by delta square partial square Vx by partial z plus square. Okay. Note that z plus is equal to delta into z, z star is delta into z plus. Okay. And then I have T star Gx star. Okay. Now, in this equation you can see that the cross stream diffusion is multiplied by a factor of 1 over delta square. Okay. Cross stream diffusion is multiplied by a factor of 1 over delta square. Therefore, it is large compared to the streamwise diffusion. Okay. This is large compared to the streamwise diffusion, and I can neglect the streamwise diffusion in comparison to the cross stream diffusion. In the convection term, you can see the deltas will cancel out on both sides, and therefore, both terms are of the equal magnitude. Okay. Both in the convection term, both terms are of equal magnitude. On the diffusion side, streamwise diffusion can be neglected in comparison to cross stream diffusion. So, I will get V x star partial V x by partial x plus V z plus partial V x by partial z plus is equal to minus partial p by partial x plus 1 by gr per half delta star square partial square V x star by partial z plus square plus t star g x star. Okay. And for convection and diffusion to be of equal magnitude, I require that this is order 1. Okay. So, I require that for convection and diffusion of equal magnitude, I require that this is order 1, which implies that delta star is equal to Grashof number to the minus 1 by 4 power. Okay. Boundary layer thickness goes as Grashof number to the minus 1/4 power in the limit as the Grashof number becomes large. Okay. And with that, the conservation equation becomes V x star partial V x star by partial x star plus V z plus partial V x star by partial z plus is equal to minus partial p by partial x plus partial square V x by partial z plus square plus t star times g star. Okay. So, that is the conservation equation with the definition of delta. So, let me write that again over here. Delta star is equal to Grashof power minus 1 by 4. Okay. And the x momentum conservation equation is V x partial V x by partial x plus V z plus partial V x star by partial z plus is equal to minus partial p by partial x plus partial square V x star by partial z plus square plus t star g star. Okay. So, that is this equation. Okay. Along with delta star is equal to Grashof number power minus 1 by 4. Okay. So, those are the two equations. The z momentum conservation equation, okay. V x star into delta star partial V z plus by partial x star. Okay. V z star is equal to delta into V z plus. Okay. Plus V z delta V z plus, okay, partial of delta V z plus by partial of delta z plus. Okay, partial V z star by partial z star. V z star is delta into V z plus and z star is delta into z plus. Okay, is equal to minus 1 over delta partial p star by partial z plus, okay, plus delta into partial square V z plus by partial x star square. Okay. because I have a delta times Vz, Vz star is delta times Vz plus. The next term I will have delta partial square Vz plus divided by partial z plus square, and I will have delta star square here, okay, into 1 over the Grashof power 1/4, okay, plus T star Gz star. Okay, this should be an x here, and in the z equation I should have Gz star. Okay. Which is the largest term here? Okay. Which is the largest term here? It turns out that the largest term is this term, the pressure term. Okay. Okay, the largest term is actually the pressure term, because it is multiplied by a 1 over delta here. Okay. So, I can multiply the entire equation by delta. Okay. I can multiply the entire equation by delta, and on the left side I will get delta square. Vx partial Vz plus by partial x plus Vz is equal to minus partial P d by partial z plus, okay, 1 by Grashof power 1/4, okay, into 1 over delta partial square Vz plus by partial z plus square plus delta partial square Vz plus by partial x star square, okay, plus T star Gz star. Should be a Grashof power 1/2. Okay. Please correct that, it should be a Grashof power 1/2 in this. Okay. And if you substitute delta as Grashof power minus 1/4, you can see that delta square is 1 by Grashof power 1/2. Okay. So, this entire term is small compared to the pressure gradient. Similarly, on the right side I have 1 over Grashof power 1/2 times 1 over delta. Delta is Grashof power minus 1/4. Therefore, this entire term is multiplied by Grashof to the minus 1/4, which is also small. Okay. And ultimately, the z momentum conservation basically reduces to 0 is equal to minus partial P d by partial z plus. Okay. So, that is the z momentum conservation equation within the boundary layer. The pressure gradient across the boundary layer in the z direction is 0. Okay. The pressure gradient across the boundary layer in the z direction is 0. That is the scaled equation in the cross stream direction. Okay. There should be a delta here as well. When I multiply throughout by delta, I should get a delta here as well. Okay. Yeah. So, the body force is also proportional to delta or Grashof number power minus 1/4. So, the only term left in this limit is the pressure gradient. Okay. So, the conservation equation becomes, okay, so I can write that conservation equation here for the z momentum. Zero is equal to minus partial P d star by partial z plus. Okay. Let us examine what this means. Okay. So, for my boundary layer, what this is saying is that there is no variation in pressure along the z direction. Okay. There is only a variation in pressure along the x direction. There is no variation in pressure along the z direction or the cross stream direction. What does that mean? That means that the pressure at any location within the boundary layer is the same as the ambient pressure. Okay. It means that the pressure at any location within the boundary layer is the same as the ambient pressure. Okay. If the ambient pressure is a constant, then there is no variation in the pressure in the boundary layer at all. Okay. So, that is what it means. Okay. Finally, the energy conservation equation. Okay, finally, the energy conservation equation Vx star partial T star by partial x star plus Vz plus, okay, partial T star by partial z plus. Okay. Vz star is delta into Vz plus, z star is delta into z plus. So, this will cancel out in the numerator and denominator. This is equal to 1 over Prandtl number into Grashof power half, okay, into 1 over delta square okay, partial square T by partial z plus square plus partial square T by partial x star square. Okay. As usual, streamwise diffusion can be neglected in comparison to cross stream diffusion, and this product delta square into Grashof power half is just 1, okay, because delta is equal to Grashof power minus 1/4. So, delta square into Grashof power half is just 1. Okay. So, the equation becomes Vx star partial T by partial x star is equal to 1 over Pr partial square T by partial z plus square. Okay. So, these are the equations. Okay. So, these are the equations. Okay. These are the equations, the dominant equations in scaled form. Subject to boundary conditions, velocity is 0 at the surface, velocity is 0 far away from the surface. Those are homogeneous boundary conditions. Temperature is 1 at the surface, T star is equal to 1 at the surface, because T is equal to T naught. That means that T star is 1 at the surface, T star is 0 far away, okay, homogeneous boundary conditions. From this you can see the solution of these equations. Since the boundary conditions are homogeneous, the temperature is 1 at the surface, 0 far away in scaled form. Okay. Equations contain only one parameter, okay, equations contain only one parameter, and that is this Prandtl number. Okay. The equations contain only one parameter, and that is this Prandtl number. Therefore, the solution also can depend only upon this one parameter. Okay. So, okay. The solution for T star and the velocities Vx star and Vz plus and the pressure, of course, it can depend only upon this one parameter. Okay. So, the boundary conditions are Vx star is equal to Vz plus is equal to 0 at, okay, z plus is equal to 0 and z plus going to infinity. Okay. T star is equal to 1 at z plus is equal to 0 at the surface, T star is equal to 0 for z plus going to infinity. Okay. So, those are the boundary conditions. So, there are no parameters there as well, okay, in scaled form. Okay. So, after we get the solution, of course, you have to solve this for a particular configuration. I will not go into the details of that. After you get the solution, you get the heat flux. Qz is equal to minus k partial T by partial z, okay, is equal to minus k into T naught minus T infinity by scaling for z is Lc into delta partial T star by partial z plus. I told you that this is only a function of Prandtl number. This solution here is only a function of Prandtl number, because the equations contain only the Prandtl number, and the boundary conditions do not contain any parameters. Okay. So, therefore, this solution has to be of the form. Okay. So, okay, this is Qz, okay, and you can get the Q average, okay, by integrating over the surface. Okay. And Q average is equal to 1 over S integral over the surface of Qz. This once again contains only one parameter, the Prandtl number. Okay. So, this has to be of the form minus k into T naught minus T infinity by L C into some function of the Prandtl number into delta star. And we know that delta star is Grashof number to the minus 1/4. We know that delta star is Grashof number to the minus 1/4. So, therefore, this just gives me Grashof number to the 1/4. And finally, the Nusselt number correlation is equal to Q average divided by k into T naught minus T infinity by the characteristic length L C. This is equal to Grashof number to the 1/4 times some function of the Prandtl number. It is equal to Grashof number to the 1/4 times some function of the Prandtl number. Okay. So, we have got the correlation down to a constant some function of the Prandtl number times the Grashof number to the 1/4. Can we say something more than that? So, can we look at the low and high Prandtl number limits of this solution? Note that the Prandtl number is equal to nu by alpha, the ratio of thermal of momentum diffusivity and thermal diffusivity. What does low Prandtl number mean? Momentum diffusivity is much less than thermal diffusivity. So, therefore, heat will diffuse further away from the surface than momentum. Heat will diffuse further away from the surface than momentum. So, if I have a surface, a heated surface, if I have a heated surface, cross stream coordinate, I will call that as Z. The momentum boundary layer thickness, the momentum boundary layer thickness for the velocity, this goes as Grashof bar minus 1/4. However, there is a thermal diffusion is much faster. So, the thermal diffusion, the temperature field decreases over a much longer distance. So, the temperature field decreases over a much longer distance, and that thermal diffusivity, the thermal boundary layer thickness goes as Prandtl number per minus half times the Grashof number per minus 1/4. So, the momentum diffusion is over a much smaller distance, thermal diffusion is over a much larger distance. Can that tell us what is the scaling of the Nusselt number with the Grashof number and the Prandtl number? So, this I will continue in the next lecture. So far, we have reduced this to just a Nusselt number as Grashof number to the 1/4 times some function of Prandtl number, and we are trying to look at different situations where the Nusselt number, where the Prandtl number is either small or large. I will continue this in the next lecture to look at the specific cases of high and low Prandtl number. I will continue this next class. I will see you then.